Hi, this is your midterm review guide and practice. So we want to go through a few things here and try to help you out with some of the ideas that are going on. Some of it I'll have you read, but some of it I'll go through some examples too. So hopefully this will be beneficial for you to get through the study guide. First of all, we're going to go through polynomials, nature of roots, and end behavior. So if I have an odd degree function, when I have a polynomial of this form, ax to the n plus bx to the n minus 1 plus plus some constant. This is the form that I'm looking at. So when I'm looking at this leading coefficient, that will tell me a lot about this. And if this degree is odd, not necessarily an odd function, but just this degree is odd, we'll have the following situations. If a is greater than 0, what we'll have is some function that might look like a cubic. Something like that. Now it might have different things going on here. In fact, I could make this dotted because I don't really know what's going on there. But your end behavior will start from negative infinity and finish off at positive infinity. If a is less than 0, then what we're going to end up with is something that goes the other way. And once again, if it's not a cubic, I don't know what that behavior is inside there, but I do know my end behavior. If it's an even degree polynomial, if a is greater than 0, we're going to get this, and then I'll put the dots in here, some parabola type thing, and it might have more waves in there. I hope you understand what these dots mean. It's just that I could have many, many zeros depending upon what this degree is. And then if I have a less than 0, then my end behavior will be like this. Okay, so that tells me a lot about my function. So you can look at this degree and this number, leading coefficient test, to see what the end behavior would look like. That will help you plot some of these graphs. Zeros pass through the x-axis unless they are double roots. Double roots will bounce off the x-axis. So in other words, this one would be an example of one that passes through. That means that it might be like x plus 2 to the cubed. You could have it to the first or to the cube. And then if I wanted to bounce off something, so then this might be x minus 3, then it raised to an even power. So this might be an example of something like this. If it is actually cubed here, though, it would flatten off, but it does pass through. If this exponent's odd, passes through. Even for the zeros, then it would bounce. Okay, even and odd functions. Even functions are symmetrical about the y-axis, where f of negative x is equal to f of x. Odd functions are f of negative x is equal to the opposite. And once again, what happens with this, if it's even, if I have a point over on this side and call this AB, then I'm going to have a corresponding point over here, which would be the opposite of A, comma B. If it's odd, I'm going to change the signs of both. So if this is AB, then this would be the opposite of A, opposite of B. Okay, and that's what this is bringing out to us. Odd, even, or neither. Prove if necessary. I'm not necessarily going to prove too much. But if I look at this, what's my degree? Well, this would be odd, and this would be odd. And so overall, I do have an odd function here. How can we show this? Well, if I put in the opposite of x, and I get the opposite overall. And so this thing right here, negative to the third, is going to be a negative. And then this negative is going to change that. If I look at this, this thing's going to be the opposite of what I started off with. And so I start off with x cubed minus 2x times negative 1. That's my negative f of x. And so this would show me that it's an odd function. This one has all evens. What happens when you plug in negative x here? Well, the negative will go away. And so we'll be left with just what we started off with. So this one would be even. Sorry, this one would be odd. So this is even. This one, I have an even and an odd together. Straight away, that tells you that it's a neither. What's the cosine? Is that odd or even? Well, cosine starts high, goes like this. And if I go backwards, it goes like this. And so here's my point AB, and here's my point negative AB. So with this one, this is an even function. And so what happens too is that tells me that the cosine of negative x is equal to the cosine of x. That will be an identity that we'll get later. For the sine function, graphically, And remember, graphically, if it's an odd function, we spin it 180 degrees onto itself around the origin. So if I put my pencil there and spin it, it's going to spin onto itself. Okay, so this one's going to be an odd function. What does that tell you? Well, if I take the sine of negative x, that means that I'm going to end up with the opposite of the sine of x. Now, what about the tangent? What happens to the tangent? Well, isn't the tangent the same thing as sine over the cosine? And so when I do this, if I plug in a negative x here, I'm going to get negative sine. When I plug in a negative x here, I'm going to get positive cosine. Well, what's a negative divided by a positive? Well, that's going to overall give me a negative. So what that tells me is that the tangent of negative x is going to be equal to the opposite of tangent of x. I skipped some steps in there, but hopefully you're picking that up. So that means for me that the tangent function is an odd function. And remember that if we take an odd divided by an odd, that kind of like a negative divided by negative, this turns out to be even. Even divided by odd, it's kind of like a positive divided by a negative, and so this would be an odd function. And even divided by even, it's like a positive divided by a positive, so we end up with an even. Okay? So you should know these rules. When I say division, it's the same thing as multiplication. If I take an odd times an odd, that would be an even as well. So those are some things that you should know. All right, rational functions. Lots of information right here. You should go through this and read. I'll probably follow here too, though. But finding zeros. Zeros come from the numerator only. Okay, and a rational function is a numerator and denominator. And so numerator only, that's where we get our zeros. Vertical asymptotes occur where the denominator is 0. That's not always true, though, because if there's a value that makes both the numerator and the denominator 0, there will be a hole in the graph. And as we said, the hole in the graph is formed when the numerator and denominator both have the same factor. And then horizontal asymptotes, this is what we call your end behavior. So we use the limit notation here. As x goes to infinity of f of x, or x goes to negative infinity of f of x, will determine the horizontal asymptotes. So let's jump into some samples here. Okay, so zeros. Zeros come from the numerator, so I hope you can see this, but x would equal positive or negative 2. Vertical asymptotes come from the denominator, and you have to write this as an equation. Please don't tell me that the vertical asymptote is square root of 2. It's not. X equal to square root of 2, and in fact we'll get plus or minus square root of 2. Make it an equation. Same thing with horizontal asymptotes. How do we determine the horizontal asymptotes? Well, if it's the same degree, we just take the leading coefficients. And so it's 1 divided by 1. So the horizontal asymptote is y equal to 1. Any holes? No, we don't have any factors that cancel, so there are none. If we look at this one, we need to factor. So here on the side, I factored my y. I get x minus 2x plus 2, and then 2x plus 3, and then x minus 2. If I look at this, I have two factors that can cancel. This one and this one. And so what happens is that this behaves like x plus 2 over 2x plus 3 everywhere except for at x equal to 2. So that's where we're going to end up with a hole. So first of all, our zeros. You don't include the hole as one of your zeros. So this would be x is equal to negative 2. Your vertical asymptotes, that's our denominator. That would be x is equal to negative 3/2. Horizontal asymptotes, you look at leading coefficients. Oh, it's x squared. Okay, that's the highest degree. So then I'm going to end up with 1/2. So your horizontal asymptote is going to be y equals 1 over 2. 1 over 2. Now your hole. Your hole is going to occur when we've canceled this factor, so it's going to be at x equal to 2. Moreover, if you want the actual point, where do you draw this little hole? And on your graph, you should put an open hole. Well, you take the x-coordinate and you put it into the function that this thing behaves like everywhere except for at the hole. So in other words, you put it in what's left. So you take the 2, put it in here, I get a 4. Put a 2 in here and I get 7. So this would be 4/7. That would be your hole. Looking at this one, zeros. Oh, that's easy. Numerator gives me x equal to 0. Denominator. Ooh, I don't see any value of x that makes that 0. Oh, we don't have any vertical asymptotes. Oh, that one's going to be interesting. Graph that on your calculator and see what it looks like. Highly recommended. Then horizontal asymptotes. Well, if you look at this, the degree of the numerator is less than the degree of the denominator. So that means the denominator is growing faster as x gets really big. More so than the numerator. So what this thing would be is 0. And so I say the horizontal asymptote is y equal to 0. Wholes, anything factor cancel? No. Okay, sine over cosine. What are the zeros? Well, that's when the sine of x is equal to 0. On the unit circle, it's going to be here and it's going to be here. So I'm just going to say that this is going to be 0 plus pi. So x is equal to, and I could go plus another pi plus another pi. So this would just be n pi. That's how we would represent it. Then vertical asymptotes would be when the cosine is equal to 0. When's the cosine equal to 0? So the cosine would be 0 here and here. So if I go to pi over 2 and differ by pi every time, then I'm going to end up with my vertical asymptote. So this is going to be x is equal to pi over 2 plus n pi. I don't need 2n pi because I just need one of these values and they differ by a pi units. Your horizontal asymptotes, I don't think there are any because the limit as x goes to infinity, these things fluctuate and oscillate, so there is none there and there are no holes. Look at this one, number 5. This is interesting. Zeros. Well, this one's going to be a little bit different because we don't have a common denominator here to I don't have this as one rational expression, so I just can't take the numerator and set it equal to 0. I have to set this whole thing equal to 0. So I'm going to get a common denominator and come back to, okay, I'm back. Here is a common denominator. I took the 5 and put the x minus 2 in there and then simplified it. So I get 6x minus 7. Double check my work to make sure I did that okay. Now if I wanted the zeros, now I can go ahead and find them because the numerator would be the value of 7, 6. So that would be the 0, the thing that makes the numerator 0. Vertical asymptotes, that looks like x is equal to 2. Horizontal asymptotes. Oh, this one's interesting. Now if I do it right here, this is easy because the numerator and denominator are growing at the same rate, so I get a 6. However, looking at it like this, how could I do it looking at it like this? Well, this rational expression, as x goes to infinity, would approach 1. Oh, what's 5 plus 1? 6. Oh, okay, yeah. So y is equal to 6. And looking at the original is because 5 plus 1. And looking at the simplified version, you could just read off the 6 off of there. Either way works. Anything cancel in the numerator and denominator for a whole? Nope. So there is no whole. All right, so there's some examples. You can use your calculator to graph some of those and see what they look like. I'm not going to spend time here doing that. Slant asymptotes. This says it won't be covered on the final. I'm going to cross that off. That definitely may be covered on the final. You will find the slant asymptote when the degree of g of x is 1 greater than h of x. And so when you divide this with long division, the quotient is the slant asymptote without the remainder part. Okay, so I'm not going to go through all this, but if I have this function, this is a rational expression, degree is 1 higher than the denominator. So when I divide these, quadratic divided by linear is going to give me a linear. That's what it's going to look like way out there. And that's the behavior. So when I do long division with this, and I trust that you can do the long division, remember you subtract with this, I end up with a remainder of 3. I disregard the remainder of 3 because as x goes to infinity, putting 3 over x minus 2 would make that term go to 0. So I just take the 3x plus 4, and that would be the equation of my slant asymptote. And that would be the end behavior. Oh, quadratic divided by linear gives me a linear. Oh, makes sense. Okay, good. All right, then other function manipulations, translations, transformations. Translations are slides, and transformations can be any type of change. So a translation is a transformation. So write the equation given that this parent graph is y equals square root of x. Now it looks like it's the same shape as a normal sideways parabola. If I go up 1 over 1, up 2 over 4, yeah, that seems like a normal shape. So I don't think I did any scale change on this. All I did was change to this new vertice. So this would be 2, 1. So putting that in here, I can go y minus 1 is equal to, my change on my x would be x minus 2. If I put this all on one side, square root of x minus 2, and then I can go the plus 1 out here because everything shifted up 1. Either way you can use to write these. It's what value of y makes this 0? Oh, 1. What value of x makes this 0? Oh, 2. Nice, works out. You should know that. Compositions of functions, putting one function into another. And remember that if we have this circle notation, I always like to think of this as a left bracket. And then you can go ahead and cover it up. And that's what you end up with. Circle, left bracket. So the g function goes into the f function. Inverse functions just means that you switch the x and y's. Okay? Also, the composition of inverse functions yields x, no matter which way you compose them. You should be able to prove these. Go back and look at some of your notes for that information. I'm not going to prove them here. Okay, first of all, find the inverse of g. So if I find the inverse of g, that means to switch x and y. So I'm going to go x is equal to y minus 3 all over y minus 7. Cross multiply x, y minus 7 is equal to y minus 3. I got y's all over the place. I got to solve for these. Well, the best way to do it is get all your y's on one side and everything else on the other. So what I'm going to do is I'm going to distribute this first. So I put the x into both of those, and this is equal to y minus 3. Then bring the y's over. So this would be minus y. And get rid of the 7x to the other side. So I end up here. Now that I got my y on one side, or my y terms on one side, I factor it out. That's the key right there. Factor out that y. And then so y is equal to 7x minus 3 all over x minus 1. That would be your inverse function for g. So you better write it as such. G inverse of x is equal to 7x minus 3 all over x minus 1. Then the next one says, please do a composition. Which one do I put into which one? This would be the same thing as f of g. So just realize that notation. And so this means that wherever I have the f function in an x value, I'm going to write down big parentheses. Oh, and I should even make them bigger than what I have. And then what do I put inside? Well, I put in the x minus 3 all over x minus 7. That would be the g function going into the f function. And then I get x minus 3 all over x minus 7. I'm going to let you simplify that. However, to clear the x minus 7, which are the compound denominators, the thing that you should do is multiply everything on top by x minus 7. Don't forget to distribute it to here. And then do this as well down here. So I'm multiplying everything by 1. X minus 7 over x minus 7. That will cancel out your compound fractions and make it easier to solve. Find f divided by g. And so I'm just going to give you the answer here. Division means multiply by the reciprocal, and there's nothing that could cancel. Remember that the full terms have to cancel in order to be able to do that. F plus g, got to get a common denominator. Try that and I'll show the answer. So I got a common denominator here by multiplying this one by x plus 7, this one times x. And then never expand the denominator. I see students trying to expand the denominator, but once you got it, just leave it. But the numerator you have to expand and combine like terms. And then you should see if this factors or not, and if it factors and can cancel. I don't believe that one does, but double check. Average rate of change. This one's key. This average rate of change is what we call slope. So if I find the slope between 2 points, I'm in business. Now what you'll see is something like this. Find the average rate of change of this function on the interval from 1 to 3. With that, that means that you need some points. These are not points. These are x values, and that confuses students sometimes. So what happens is that I get 2 points. 1, comma, I don't know. And then the other one's 3, comma, I don't know. We got to find those I don't knows. So I'm going to take each one of those and plug it into my function. So if I plug in 1, so taking the 1 and plugging it in, I believe I got 0. Hopefully I did this right. And then 3, take it, plug it in, you get 10. So now I have my 2 points. My average rate of change would simply be the slope. So it's 10 minus 0, y minus y, over x minus x. So this would be 10 over 2, which is equal to 5. And so when we do average rate of change, a lot of times it's associated with units. And so this might be your meters, and these might be your seconds. What's meters divided by seconds? Well, meters per second, or miles per hour, whatever it might be, but that would be your average rate of change on an interval. Find the average rate of change of something like this. So I have the same function, but I have these 2 points. Oh, these are a little bit weird. This sets you up for calculus, however. So I do kind of the same thing. If I do my x value, I'm going to get this whole function. So this would be 2x squared minus 3x plus 1. So just like I did here, I found the y value. Here, if I do x plus h, this is going to be a little bit more funky. So I'm going to go x plus h, quantity squared, minus 3. Wherever I have the x, I put parentheses, x plus h, and then plus 1. So here's a x, here's a y, here's a x, here's a y. Average rate of change, find the slope. So I'm going to simplify this and come back to you. Okay, so what I did was I took the y coordinate from here and I subtracted the y coordinate from this other set of coordinates. And then down below I took the x plus h and divided by, or subtracted x. Now if I simplify all this, I don't know if I got room in here. We'll get it going though. So I remove the parentheses here by shooting the 2 in for this function, or this piece, and then negative 3 into here. And now if I look at all this, I can cancel. Look at this, 2x squared. Boom. 3. Look at negative 3x. Did I make a mistake there? Sure did. What did I forget when I did this minus? Well, it should be minus all of these things. So this should be minus 2x. This should be plus 3x, and then minus 1. Make sure that you distribute that negative. I did that on purpose, right? And then so I get negative 3x plus 3x, and then this 1 will cancel. So all I'm left with then is 4xh plus 2h squared minus 3h all over h. Then I can do my bunny rabbit. If I have this on the bottom and it goes into all the terms, then I can cancel that. So then this would be left with 4x, the h cancels, plus 2h's, and then minus 3. There you go. So that would be the average rate of change of this function on the interval from x to comma x plus h. Both of these are x coordinates. Find the y coordinates and then go plug and chug. Okay, the next topic, domain and range. With domain and range, well, for domain, we mostly will be concerned about looking at those values and the domain issues. Range, we probably want you to look more at a graph, but with sinusoidals, you should know that, and logarithms and some other ones that we do have. You should say exponentials. And you should have a general idea of domain and range. More specifically, domain than range, but you should be able to look at a graph and tell me what the range is. So with this one, this example, we want to find the domain of this function. Well, the domain issues are a couple things. In the denominator, I have a square root. So with square roots, I can't have anything that's negative underneath. And I also can't divide by 0, which would be another issue for this one. So what happens is that I got to find the 0 of the denominator. 7x minus 1 is equal to 0, so x is equal to 1/7. And do I have to be greater than that or less than that? Well, for instance, if I plug in 1, oh, I'm okay. So I need to be greater than 1/7. Now, if this was just a square root function, I could put the equal here. But since the square root function is in the denominator, I have to also consider the denominator. And so I can't divide by 0, so it's just going to be x is greater than 1/7. That would be your domain. All right, optimization. Find the maximum or minimum. Optimization, you want to get one equation, which we call the primary equation, and then we need to get a secondary equation, which will help us solve this. For instance, I want to find the maximum area of the rectangle that's inscribed, and I want it in the first two quadrants too. So if I take the area of this, and remember that this point is x comma 9 minus x squared. First of all, I need an area formula. What some students forget is that this is x, but I'm looking at this rectangle. There are two x's. So my overall formula is going to be a is equal to 2x, and then times my height, which would be y. Now this is what we call our primary equation. Now the secondary equation will help us get this whole thing in terms of x. Well, I need to get rid of that y, and I hope that this is obvious, but they tell us what y is. So y is equal to 9 minus x squared. This is my secondary equation. Overall, put into the primary equation, I should be in business. So what happens is that this is the equation that we want to optimize. A is equal to 2x. Now instead of y, I'm going to replace it so I got everything in terms of one variable. This means area in terms of x. That means I solve for area in terms of x variables. Then what you would do from this is that you would go to your graph, find an appropriate window, and find the maximum. I'm not going to do that for you here, but that's what you need to do. I changed my mind. I will show you. So if you get this graph, this is a standard window. Where are we looking at this? And what is your practical domain? Well, I'm looking at x in the first quadrant, and x can go up to a value of, what do you think? 3? Yeah, makes sense. Okay, so if I do this, I should fix my window a little bit. And so I'm going to be smart about this and go to Window Settings. And I can start this at -1 just to show a little bit. I don't need too much of this one, so I could change that. And then my y max, well, it definitely has to be bigger than 6. So maybe I go to 25 just to be safe. And there's my graph right there. And then I can calculate the maximum by going to Analyze Graph. If you're on the 84, then you can go second calculate. Here's your maximum. And you just have to pin this thing in. So lower bound is on the left of it. Click. And then there's my maximum shows up. So I just go to the right. And there's my value. If you're not getting enough of these values, you can go over the top of it like this and push your plus sign, and you get a lot more decimal places. So actually, I can take a few of these away if I want. Did it take any away? I did minus. Oh, it doesn't look like it's working. I don't know why. Okay, so you just go over the top and then do plus or minus depending upon how many decimal places you want. So what does this mean? Well, that's my x value. What does the 20 mean? Oh, that would be your maximum area that you'd be talking about. So answering this is my maximum area. Where did it occur? X equal to 1.732. Okay. Exponential functions. Let's get some examples here. What's the domain of this function? No domain of exponential functions too. So if I do the domain, if I graph just y equals ln x, that's going to look like this. Goes all the way down. This point right here is 1, 0. What's going to happen then is that this is going to be translated how? Well, I think that looks like a left 1 to me. So instead of having a vertical asymptote at 0, I'm going to have a vertical asymptote at x equal to -1. And so this will start way down here, and we'll go through this point. I end up with that. What is this point? Well, this one will be 0, 0, because I shifted left 1. So my domain is going to be x greater than -1. Your range for the logarithmic functions should be all reals. This will keep on increasing. Looks like it flattens out, but it doesn't. It keeps on going up and up and up. Next question. Don, he has this money to invest at 6% for 4 years, compounded monthly. Remember these formulas. A is equal to P, 1 plus R divided by N raised to the NT. If you need more information on all these, go back and watch the full video. But this is the formula that we want. This would be N is equal to 12 because we said monthly. N is based upon how many times you're going to compound over the course of the years. So this amount would be your principal, 5,000, 1 plus your rate, which is 0.06 divided by 12, raised to the NT. So that would be your 12 times your years. So that would be 12 times 4. So this would be part A. I'm not going to find these answers. I trust you can do that. Part B, compounded continuously. Then we're going to use PERT. Whenever it says continuously, you think PERT. So then this would be equal to your 5,000, and then this would be e to the r, 0.06 raised to the, or times t. So this would be times 4. Once again, put that in your calculator. It should be a little bit more than this, because if I'm compounding continuously rather than monthly, then I'm going to end up with more money. When will the investment triple? This is always a tricky one for some students. And so if I start off with 5,000, and it depends which formula you're going to use. I'm going to use the PERT formula. So if I use this formula, 5,000 e to the 0.06 times t. We want to find t. When will it triple? 15,000. So if I want to solve for t, what I have to do is get rid of some of these other values. So I'm going to divide by 5,000. And since I'm tripling, look at what number I'm going to get over here. Oh, I'm going to get 3. Oh, that makes sense. E to the 0.06 t. And then what I need to do then is I need to take and do a ln. I need to get this variable out of the exponent. This side it will cancel, so I have ln 3 is equal to 0.06 t, and then I just divide both sides by 0.06. I think my computer is overloading, so I'm going to end up with that. So your time would be ln 3 divided by 0.06. You can go and calculate that and figure out what that is. Okay. Now for trig, and these are just sample examples. There'll be a lot more that you'll have to know for the exam, but this will at least get you going. For the trig, we want to find the exact value of this, sine of 5 pi over 6. So what I do is I draw my picture. I see that it's a 30, 60, 90 lying down. And what that will tell me is that the y-coordinate, since it's sine, y-coordinate is 1/2. And so this is equal to 1/2. That's examples that you have to do. You have to be good at that. Do that fast, then that saves time for the rest of the test for you. Sine of theta is equal to negative square root of 3 over 2. If I did this one, this would be the y value being the big negative here. So it would be the triangle lying down. So I'm going to end up with two values of theta here between 0 and 2 pi. What are those two values? So this one would be 4 pi over 3. And this one around here would be 5 pi over 3. But it does say all values, so I have to kick around the unit circle more times. So this would be 2n pi. So from 4 pi over 3, I got to go around. Go around. That's what the 2n pi does. And then do the same thing for 5 pi over 3. Okay? Then the last part here. Write the equation of the sinusoidal. And also applications. There'll definitely be applications on the test. So if I look at this one, you got to decide, do I want a starting point here, which I'd write a negative cosine function for, here, which would be the sine, or here, which would be the positive cosine? I think that I probably want to do this one right here. I can show you the other ones too. So the general form is y is equal to a cosine or sine, and then the nested parentheses, which helps us get this whole thing taken care of. So if I look at the amplitude, this is hard to see maybe, 1, 2, 3, 4, 5, 6, 7, 8. My max, it looks like 8. And my min looks like -2. So overall, this distance is 10, so A would be 1/2 of that distance, so that would be 5. And so your A value is 5. If I do my D value is adding these two and dividing by 2. So that would be 6 over 2, which would be 3. So those would be my two values that I can get right away just from the max and min. Then you got to figure out your period. Well, the period is how long does it take before it starts repeating itself. So take two corresponding points, measure this distance. So the period is equal to 10. That's what I counted. If the period is equal to 10, a lot of students like to take this 10 and put it in there. No, you just found the period. How long does it take before it repeats? You need to find B. So B, this is the peanut butter equation. So this would be 2 pi divided by 10, which is your pi over 5. I'm going disco with the things going on and off. And so this would be A is equal to 5 cosine B, which would be 2 pi over 10, or else you could go pi over 5, x minus c. Oh, I haven't done that yet. And then I go plus d. Now, what happens is that since I'm writing an equation with positive cosine, I'm finding the horizontal distance from the axes, the y-axis, to my starting point. My starting point is considered to be the high point because that's where the cosine function usually starts. So if I count here, 1, 2, 3, 4. This shift would be 4, so I put x minus 4 there. Now we could write this different ways too. If I wanted to write this with a negative cosine, what happens is that I would need to start at the low point and figure out the shift from the y-axis. It's going to be this way. So I would put negative 5, this stays the same, cosine 2 pi over 10, and then it would be x plus 2. Why x plus 2? Because, I'm sorry, x plus 1. Because this shift is left 1. And then this would be plus 3. That stays the same. These two equations turn out to be the same. You can graph them. So these are two equations. One's positive cosine. We start at the top. I could start here too and find that shift if I wanted to. These are phase shifts, and so you could do different phases. Then this one is negative cosine, so I start down here. If we wanted to write one with sine, we'd have to find this middle value. Looks like it's 1.5, but I'm not certain. You could figure that out. And then you could start there for a sine graph if you wish to. Then that would be slid over about 1.5. All right, I hope this helps you for the final. Make sure that you study a lot and get through the packets and do problems. That's the main thing, always do problems. Thanks a lot. Good luck.